you apply them. That's a very important property. The limiting operation and the function operation commute. Okay. Okay. Very cool. So, question. Is this function continuous? Two points. I'll let it be whatever I want on one and whatever I want on the other. Take a second to discuss that with your neighbor if necessary. Is it true that for every epsilon, okay, well, there's only 2 points to check whether it's continuous at P. So do you want to check that it's continuous at this point or this one? Doesn't matter. We'll just do this one. How does this one, okay? Is F continuous here? Is it true that for every epsilon you name, there's a delta around which, as long as you're within some delta of P, you're within some epsilon of F of P? You give me an epsilon. I don't care which one. How about this one? Can I find a delta around P so that everything in here, that's also in E, also lands in here? Yes. So is this function continuous? Yes. The delta ball has nothing else in it except 1 point. Oh, this is also continuous. This function is continuous. Very interesting example. Okay. Question? Oh, no, it wouldn't be. Not a very good question. Because I'm demanding that everything be within some distance of the image, right? So we're not looking at this definition. We're looking at this one. So there's only 1 point you could be talking about, f of P. Does that help? So automatically, if you take a function from a discrete metric space to another metric space, it's automatically continuous. That should make some intuitive sense to you, right? Because discrete metric spaces, points are all separated, right? So you vacuously can't approach points, right? So clearly satisfies the definitions. Excellent. Okay, well, what does this mean? Well, like before, sums and products and quotients of functions are all continuous. It follows from the theorems about limits. So sums, products of continuous functions are continuous. Again, we're talking about now when y is r. Quotients are continuous as long as the denominator is what? As long as g is not 0. Then the quotients are going to be continuous as well. All follows from those results. Okay. Let's see. Here's another corollary. What about vector valued functions? Suppose I map a metric space into a vector, and the functions are, oh, they all have components, f1, f2 through fk, or f, in this case, yeah, k. Here's a theorem that's handy. I claim one way to tell if f is continuous is just to check what? If all the fi's are continuous real valued functions. Okay, each. That's a nice little fact. Again, sums and products are continuous as vectors. Oh, yeah, B is different because these are vector-valued functions, and this is a dot product. And this is just a regular sum, but a sum of vectors. Okay. Yes, excellent. Okay, let's see why this is true. again, should not be hard to see why this is true. Ooh, I want to keep those definitions. Let's do that over here. Why is A true? Well, you just have to do some bounding. So this is the proof idea of part A. You want to go forward or backwards? Your pick. Well, let's just do one direction. So would you agree I can bound? In one case, would you agree I'm trying to make the distance between f of 2 points small, right? Distance between f of x and f of p small, right? In one case. The other case, I'm trying to make the distance between fi of x and fi of p small. So if I have that one is small, can I show the other is small? Well, yeah. Wouldn't you agree that the distance between fi of x and fi of p, this is now in the vector space, or no, in the real valued, this distance, fi of x and fi of p, would you agree that this is this somehow related to the distance between f of x and f of y? Yeah, this thing has components of that look like this, doesn't it? This is always bounded like that. So you just use this fact, right? So you want to make this smaller than epsilon? You do it exactly when you make this smaller, and that will make this smaller than epsilon. Good shape. So the same delta will work. I'm just giving you the basic bound. Now, what if I have this and I need to make it small, and I know this is always small? Well, if you know all of these are small, isn't this just some combination of all of these? Yeah, it's the sum of the fi of x minus fi of p. And then I take the whole thing and I take the square root. And I square these, I guess. I goes from 1 to n to k. So this actually equals this. So if all these are small, you can make this small with some good choices of epsilon, etc. Okay, so this is basically where the bound comes from. And part B just follows from using components in part A. Okay. Very, very cool. So, what do we know? What do we know so far? Well, we know what it means for a function to be continuous. We have two different characterizations of continuity. We have a characterization involving epsilons and deltas. You give me an epsilon, I'll find you a delta. We have a characterization involving sequences, which we already understand. Turns out there's still a third characterization of continuity. And this one is perhaps not at all obvious. But I will describe it now, and then we'll try